Welcome to today's paper reading. Today's paper is titled, Multimodal Table Understanding. This paper was published on the AR14 preprint by Mingyu Zheng and colleagues from the Institute of Information Engineering, Chinese Academy of Sciences and Baidu Inc. The abstract highlights the limitations of current table understanding methods, which heavily depend on converting tables into text formats like Markdown or HTML. This conversion process is not always feasible in real-world scenarios where high-quality textual representations are scarce, and table images are more readily available. To address this, the authors introduce a new problem, multimodal table understanding, where models must generate responses based on table images. They create a large-scale dataset, MMTab, to support this task and develop Table LLM, a multimodal large language model. This model significantly outperforms existing baselines across 23 benchmarks, demonstrating its effectiveness. The code and dataset are publicly available for further research and development. Tables are extensively used across various fields such as financial analysis and scientific research. To maximize the utility of tabular data, the table understanding technique has been developed to automate tasks like question answering and text generation. This technique significantly enhances work efficiency but has faced challenges, particularly with large language models, LLMs, that rely on text-only input. These models struggle with visual tables and the need for visual information. To address these issues, the multimodal table understanding problem was proposed, along with the construction of the MMTab dataset and the development of the Table LLM model. This approach aims to improve the understanding and processing of tables using visual information. Figure 1 presents an overall performance comparison of Table LLM 7b against existing multimodal large language models, LLMs, on various benchmarks for multimodal table understanding. The figure highlights that Table LLM 7b significantly outperforms recent open-source LLMs and demonstrates competitive performance with the powerful GPT-4v across most tasks. This comparison underscores the effectiveness of Table LLM 7b in handling multimodal table understanding tasks, showcasing its superiority in this domain. The table understanding (TU) problem focuses on automatically extracting, transforming, and interpreting essential information from tabular data. This has attracted significant attention in recent years. Various tasks fall under TU, such as table question answering, TQA, table fact verification, TFV, and table-to-text T2T generation. Different approaches have been proposed to solve these tasks, ranging from early rule-based systems to later tabular language models, LLMs. However, these methods are limited to specific tasks and table types. Recently, large language models, LLMs, have been enhanced with strategies like prompt engineering and instruction tuning, leading to models like TableLlama and TableGPT. Despite these advancements, previous TU approaches, including tabular LLMs, are unable to directly understand table images, limiting their application scenarios. The MMTab dataset is composed of samples from 14 public datasets across 8 domains, covering 9 representative academic tasks. These datasets include tables in various textual formats such as HTML and Markdown. To facilitate multimodal learning, the textual tables are converted into high-quality images using Python scripts. The task-specific input and output texts are formatted into an instruction-following structure, with additional instructions to ensure the final answer is output in JSON format. To enhance the robustness and diversity of the dataset, various data augmentation techniques are applied at the table, instruction, and task levels. This includes rendering tables in different styles and generating diverse instruction templates to simulate real-world variations. Figure 2 illustrates MMTab, which includes a variety of table images and instruction-following data, addressing a broad spectrum of tabular tasks as detailed in Table 1. This diversity in data types and tasks is crucial for enhancing the performance and versatility of multimodal learning models. Figure 3 provides an overview of the sample construction process for multimodal instruction tuning. This process involves creating final samples with a unified format of table image, input request, output response. The construction adheres to the original dataset partitioning, selecting 11 datasets for training and held-in evaluation, while 3 small-scale datasets with non-overlapping domains are used for held-out evaluation. Figure 4 illustrates the 2-stage training tasks and evaluation process of table LLVA. The first stage involves pre-training the model on a large dataset of table images and their textual representations. The second stage focuses on instruction tuning, where the model learns to follow specific instructions related to table understanding tasks. The red font highlights the contributions made in this study, which include the development of a versatile tabular multimodal large language model, LLM, named Table LLVA. This model is designed to enhance the understanding of table structures and is trained using an enhanced 2-stage procedure. The evaluation phase includes 6 tasks aimed at assessing the model's basic understanding of table structures, providing a comprehensive testbed for MLM research. The Table LLVA model is composed of 3 main modules. A pre-trained vision transformer (VIT) model serves as the visual encoder. A 2-layer multi-layer perceptron (MLP) acts as the vision language connector, and a vicuna model functions as the large language model (LLM) backbone. During the pre-training phase, the vision language connector is trained on the MMTab pre-dataset with a table recognition task, which involves generating textual table representations that include both table structure and content. This step aims to align visual features with ground truth textual representations, enhancing the model's ability to perceive table structures and perform optical character recognition (OCR). In the instruction fine-tuning stage, the pre-trained vision language connector and LLM are jointly fine-tuned using multimodal table tasks from the MMTab instruct dataset and traditional multimodal tasks. This stage aims to address the gap in multimodal table understanding and improve the model's generalization by including the original pre-training and fine-tuning data of LLVA 1.5. The influence of these components is analyzed in the ablation study. In this section, we discuss the baselines and methodology used for our experiments. We consider 3 types of baselines: open-source multimodal large language models, MLMs, open-source large language models, LLMs, and GPT-4v with different image resolutions. For evaluation, we use various metrics such as accuracy and BLEU for tasks like table question answering, TQA, table fact verification, TFV, and text-to-table, T2T. Additionally, we compute cell-level F1 scores for tasks like multimodal cell detection, MCD, and row/column extraction, RC, and use the triedit distance-based similarity, TEDS, score for table recognition, TR, tasks. Our methodology includes a zero-shot setting, comparing Oracle-provided table sequences with those recognized by OCR, and a detailed comparison with GPT-4v to assess performance. Table 2 presents the evaluation results of various models on 11 held-in academic tabular benchmarks. The table compares the performance of models when provided with ground truth, plus Oracle, or OCR extracted, plus OCR, textual table representations. It highlights the performance of different models, indicating those that have been trained on the corresponding datasets with, and results from original papers with. This evaluation helps in understanding the capabilities and limitations of current models and multimodal table understanding tasks. Table 3 presents the evaluation results on 6 held-in table structure understanding benchmarks. The table highlights that higher values in the evaluation metrics signify better performance. It also notes that the target textual table representations in the table recognition task are in HTML, Markdown, and LaTeX formats, with TEDS as the evaluation metric. For detailed information, refer to section 5.1. Table 4 presents a comparison of Table LLVA with GPT-4v across 24 benchmarks, showing that GPT-4v achieves better results on 10 of them. The lower section of the table details ablation study results, highlighting that the removal of MMTab pre-training leads to a more significant performance drop compared to other ablations. Additionally, the study reveals that fine-tuning with mixed data is more beneficial for model performance than using data sequentially. This paper introduces a new problem in multimodal table understanding and presents a large-scale dataset called MMTab. MMTab covers a wide variety of table structures and tasks, serving as a comprehensive testbed for multimodal language model research. Based on MMTab, the authors enhance LLVA 1.5 to create Table LLVA, a generalist tabular multimodal language model. Experimental results indicate that Table LLVA significantly outperforms existing multimodal language models on multiple benchmarks and performs comparably to GPT-4v. The paper's contributions advance research in multimodal table understanding from the perspectives of task definition, dataset creation, and model development. The study has several limitations. Firstly, the dataset is focused on single tables in English, and does not cover multi-table scenarios or broader language support. Secondly, while MMTab uses high-quality images, real-world table images can be of lower quality, such as blurred or handwritten. Future work should include more diverse images from real-world scenarios. Lastly, the input image resolution in Table LLVA is relatively low, which may limit its performance. However, with the development of LLMs offering higher resolution, future research could address this limitation. The MMTab dataset is constructed using academic datasets such as WTQ and TabFact, which are licensed under the MIT license and CC BY SA 4.0 license, allowing for free and open research use. Python scripts are employed to convert textual table sequences into image formats, facilitating the creation of multimodal instruction-following data. This process results in the MMTab dataset, which is intended as a freely accessible resource for the community to explore multimodal table understanding. The authors assert that there are no foreseen ethical concerns associated with this research. Thank you for watching.